Look at organic chemistry here. Study of carbon-based compounds. Things like not organic chemistry are carbonates, so anything with CO3 2 minus. Carbides, so that's the C2, I believe that's a 2 minus there. Cyanides, for example, CN minus, part of an ionic compound. Anything like carbon monoxide or carbon dioxide, those are examples of, those are not organic compounds. So we have to keep that in mind. All right. So carbonate, carbides, cyanides, oxides of carbon, things like that. Otherwise, there's a lot of organic compounds that we have. Carbon-based compounds often have same chemical formula that different structures. So we have propyl cyclohexane versus, so propyl cyclohexane, propyl, say, what do we got here? 6 for the cyclohexane part, 7, 8, 9. And then H's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Don't forget there's one there. 11, and then 12, 13, 14, 15, 18 looks like. So cyclohexane, propyl cyclohexane versus 2-ethyl-3,4-dimethyl-pent-1-ene. Let's see. So pent-1-ene is where you want to start here. Pent-1-ene, there's the double bond. 2-ethyl, that's 2 carbons added on, and 3,4-dimethyl, like so. And of course, filling in the rest with H's here. So H2, that one's good. And that's also C9, should be H8. We did that right. 5, 6, 7, 8, 9, yeah, carbons. 2, 4, and 6 is 10, 15, 8, yeah. So, yeah. Oh, so, no, because the double bond, yeah, the double bond makes it only 5, yeah, yeah. And it's still the longest chain with that 5, right. All right, those are called isomers, of course. Isomers have the same formula, so same formula, different, obviously different structures there, quite a bit different. All right, so those are isomers. Hydrocarbons are next. Aliphatic. So aliphatic hydrocarbons are things like alkanes, cycloalkanes, alkenes, alkynes, cycloalkenes, cycloalkynes. Aromatic, of course, has to have contain 1 or more benzene rings. And don't forget the benzene rings, of course, look something like this here, right? And they got that circle in there, basically meaning you will see sometimes it's written like this here, alternating doubles or double bonds there. Usually you're going to see the ring there, of course, but when they do that, you have to understand that that's alternating single and double bond, basically. Sometimes they draw it like that as well, but usually it's the left one that we talk about. Don't forget, when it says benzene rings, we can also include phenyl groups in there. Or benzene rings, of course, that have been added on. So that could also be part of an aromatic then. Okay. Phenyl ring, or the phenyl group, is just the benzene ring that's been added onto a chain. Naming hydrocarbons. All right. So always longest carbon chain, of course. If it's got a double or triple bond, we got to include that in the longest chain. So I'm going to go with, it doesn't really matter. Obviously, there's a few different ones you could do here. I'll go with that. I like to kind of keep it straight across there. So what is that? 1, 2, 3, 4, 5. So that's pent. Let's see, is this going to show up here? Probably not. Work on the backgrounds here. Pent. All right. On the second carbon, of course, we have the double bond. So I'm going to put my pent-2-ene there. And then once again, we have to start, and we have to once again start at the end closest to the double bond. So it's 1, 2 carbons, or I guess the other option is 1, 2, 3, and 2 of course is better. So always the double bond is the main feature there. Pentuene, and on the second carbon we have a methyl, and on the third carbon we have a methyl. So we're going to call it 2,3 dimethyl pentuene. 2,3 dimethyl pentuene for that one there. All right, this one, let's go to the right here maybe. This one here is cyclo. So don't forget the cyclo part, that's very important. This is butene. So 4 carbons, but, double bond, ene. We don't need a number with this one because remember, this one here, wherever I put that double bond, that's always going to be carbon 1, 2. Your options are, though, I guess you do have a couple options. You could go 1, 2, 3, or, of course, you could go 1, 2, 3, then that one. And you still want to use the lowest numbers possible, so we're going to go with the red ones here. 1, 2, 3. 3 has got an ethyl group, so we'll go with 3 ethyl. 3 ethyl cyclobutene. Let's see, cyclo. A lot of cyclos out here. This one here, I'll just do down here a little more. That's cyclopentane. Cyclopentane. And once again, on whatever carbon here, you're going to have this 1, 2, 3, 4 carbon chain added on. That, of course, is but. So that would be butyl cyclopentane. We don't need a number with that one because there is only that one add-on chain. So we're not going to need a number with that because obviously we're just going to assume that's carbon 1 there in that case. So butyl cyclopentane. Remember this molecule turns and stuff and whatnot. So obviously if we want, we can put that anywhere and we just turn it and matches up. This one here, of course, this is your benzene ring right there, so we're going to call this benzene. Remember, you don't need cyclo with this one. It's just benzene. That's the benzene ring. And then I would say on 1 and 3 is the lowest numbers you're going to be able to use with this one. You got dimethyls. So 1,3 dimethyl benzene would be that one there. All right. I guess next we got to do some draw rings. Draw rings. 2,4 dimethyl pentane. So I'm just going to go to the bottom here and do those. 2,4 dimethyl pentane. Start with the pentane part. 1, 2, 3, 4, 5. 2 and 4 have methyls. So 2 methyl, 3, 4 methyl, and just fill in the rest with H's, of course. Be careful when you fill in with H's. Make sure you have the appropriate number around each one because once again that's going to affect the formula and that could affect molar masses and whatnot. That would be bad. B. Methyl but-1-ine. But-1-ine, that's a triple bond, ine, and methyl. And they don't tell you anything about where the methyl is, so that right away tells me that there's probably only a few spots we can put it. We can't put it on the first one, because if we did, then we don't have a 4-carbon chain. We'd have like a, I can't put it there because then, of course, I'd have a 5-carbon chain. I can't put it on this one here because I already got 4 bonds around it. Can't put it there. I could put it here. That probably is the correct answer, actually. And I couldn't put it here because once again, so in that case, fill in the rest with H's, of course. H, that's good. Like I said, H and H3. Okay. 3-phenyl-hex-2-ene. 3-phenyl hex-2-ene. Hex-2-ene. Let's see. 1, 2, 3, 4, 5, 6. 2-ene double bond. 3-phenyl. So phenyl, of course, is your benzene ring add-on here, like so. 3-phenyl, and we'll do 3 here. That needs 1. 1, 2, 3, 4. That's good. That needs 1, 2. That needs 2, and that needs 3. All right. So there's some drawings there. And then we're going to get into some of the other ones here. Alcohols, of course. Alcohols, don't forget, of course, have this hydroxyl group is what it's called, hydroxyl group, and that's that part right there, that OH part. Alkyl halides, of course, halides refers to the halogens. So this is, of course, the halogens, and things like fluorine, chlorine, bromine, iodine are the halogens. So some carbon chain with those linked onto them, or with those halogens or halides linked onto those. Carboxylic acids contain the carboxyl group. Make sure you know these carboxyl, hydroxyl groups things here. And of course, that's your C double bond OOH at the end, of course. And then esters contain a carboxyl group. So they do have a carboxyl group. The difference between the carboxylic and the esters is the carboxylic acids, that C double bond OOH is always at the end of the chain, whereas in an ester it's in the middle, and it comes from two different parts, of course, and we know that esters are made up of alcohols and carboxylic acids. So we still got this, in fact we should probably put an R prime there maybe perhaps. We still got that C double bond OO, but it's linked to a different chain after that. So those are esters. And we'll get to that, those reactions in a bit here. So we need to name these here. Let's see. With this one here, once again, always longest chain. So make sure you find that. In this case, longest chain. Don't forget that's kind of the main feature in this one. That's the alcohol group there. So that is what? 1, 2, 3, 4, 5. And we do have to state where that alcohol group is. So that would be 5. That's pentan. Don't forget the AN there, and then 1 ol, it's on the first carbon. The OL, of course, is the alcohol part. So that's carbon 1 right here. That means that on carbon 1 I have a methyl group. On carbon 2 I have a methyl and a methyl. So I'm going to go with 1, 2, 2 methyls. 1, 2, 2 trimethyl. You'll like it. Pentan 1 ol. 1, 2, 2 trimethyl pentan 1 ol. So that one there. Let's go to the right one here. That's cyclohexane. Cyclohexane. So I'll write that down. Cyclohexane. Oh, that's not going to turn out very well at all there. That's cyclohexane. And then we need to use the lowest numbers possible. So let's see, 1, well, actually no. So our options, probably temptation is to go 1, 2, 3, because those are lowest numbers. But actually in this case here, or vice versa, 1, 2, 3. However, 1, 1 is got to be the lowest number there. So you kind of have to put this one as a 1 here, unfortunately. 1, 1 are going to be lower than any, like 2, 2, for example, or whichever way other way you want to do that. So the 1, 1 is better than the 2, 2. So 1, 1, and I'll just say it doesn't matter which way you go. Honestly, this is going to be 2, then 3, 4, 5, and that'll have to be a 6. So let's see. That is 1, 1 dibromo. Bromo comes before chloro as well, so that's good. Alphabetical, of course. Geez, I don't know if we have enough room. I'm going to write down here. 1, 1 dibromo. And then I'd have to go 2, 6 dichloro cyclohexane. So 1, 1 dibromo, 2, 6 dichloro. That one. That one's tricky. All right. Next, let's see here. Oh boy. All right. Well, once again, this part right here, right? Well, actually, technically up to there, I guess, but that part there, of course, has the C double bond O bonded to it. That's kind of the family name or the parent name. That comes from the acid. That's 1. Don't forget, when we label these carbons as well, this one here is 1. That's 2, 3, 4, 5 carbon there. So you start at that double bond O there. That's carbon 1. So let's see, that's what, 5? So that's pentanoate. This is an ester, of course. Pentanoate is that part there. And then on the other side, that came from pentanoic acid, of course. This part here is, of course, your alcohol part. That's what it came from. And that, of course, is, well, that would have been butanol, butanol actually, but butanol. But now, of course, because we have to separate these, that's called butyl. Space in between the two, of course, because that's where kind of the separation between those two. So butyl pentanoate for that one. This one here, we got a C double bond O, OH at the end, so I know that's a carboxylic acid. There's carbon 1, 2, 3, and 4. So that is butanoic acid. Start with that. And let's see, on the second carbon I got 2 chlorines, and I guess that's all I need to worry about. So let's go with 2,2-difluoro. I think I spelled that wrong. Difluoro butanoic acid. All right. And what else we got here? Oh, drawing some. All right. So these are the same ones here. Let's just double check here. Sure. All right. Good. So let's start here. 2-chlorobutanoic acid. Okay, butanoic acid. 2. There's 1 right here. That's 1. 2. What is it? Chloro. So it looks like that. That's an H there. That's a 2, and that's a 3. I guess I may just get rid of this so we don't confuse it. So that's 2 starts, of course, at the double bond with those. Make sure. B is ethyl butanoate. Okay. This one here is ethyl butanoate. So ethyl butanoate, butanoate, of course, that's the 4 carbons, butanoate part, and then on this side, ethyl. So 2, 3, let's see, 2, 2, 3. Okay. So ethyl butanoate for that one. Hexane 2,3-diol. Hexane 2,3-diol. So let's see. Hexane. That's what? 6, 2, 3-diol is what you need to have there. And then, of course, 3 there. 1, 1, 2, 2, and 3. Hexane 2,3-diol. And then, let's see. D is 1,1,2,3 tetrabromocyclopentane. Cyclopentane. 1,1. I'm going to put 1,1 here because I want to. Tetrabromo, so BR. 2 and 3. Bromine. Tetrabromocyclopentane. Okay. Good. Separation of organic compounds. So this is kind of, you know, the naming part's usually okay, you know, drawing and stuff like that. Usually it's the equations which are coming up here, and then of course this as well. So first of all, fractional distillation uses differences in boiling points to separate the different components of petroleum. So make sure you know how the fractional distillation tower works. There was a handout on that in class, of course. The highest boiling points are at the bottom, and of course as you go up, the gases cool and they start to condense as you go higher up. And the lower boiling points are up at the top there. Solvent extraction uses differences in solubilities of various solvents to separate mixtures. So polar solvents polar solvents, water. Small alcohols dissolve polar molecules. Slightly polar solvents, larger alcohols, alkyl halides dissolve slightly polar molecules. And of course, non-polar solvents, hydrocarbons dissolve non-polar molecules. All right. The important thing to remember with those, and I don't know if that's on the next sheet or not here, or maybe it's farther on here. Is it? Maybe it's not. Make sure you know the differences in with that. I guess the biggest thing is make sure you know the differences between solubility and boiling points. And that's kind of this up here as well, a little bit of boiling points there, but remember that boiling points tend to increase as basically the molecule gets larger and larger. However, when the molecule gets larger and larger, you have to remember that the polarness of that molecule actually gets smaller and smaller. So, you know, the smallest molecules that are polar tend to be very soluble, but as you get larger and larger, that polarness starts to wear off, so they don't become as soluble anymore. Boiling points, you know, the larger the compound, that tends to be the higher the boiling point. However, they are less polar. So there's some things there that you probably want to go back, and I told you guys to make cue cards with that stuff. Probably a good thing to look at for those, right? Combustion reaction. So I'm gonna switch this down and drag this. Let's just drag that right down here. All right, there we go. So 2-methyl cyclohexane. Obviously, you're going to have to probably draw these out first. 2-methyl hexane. 3, 4, 5, and oxygen. Don't forget that is a double bond there, of course. What are you going to get if they just want if they don't want a balanced chemical equation? All that, that's fine. Carbons and hydrogens are going to give you carbon dioxide and water. Okay, so that's really all you need to have for that one there. You don't need to worry about balancing it or anything like that. They just want the structural diagram basically of what that would kind of look like. Okay, so that's what you need for that. That's combustion, of course, carbons and hydrogens, carbon dioxide, and water. Next, propene and hydrogen. Let's see here, I'm just going to sheet down. Propene, the first one here. I'll just leave 1A here. Propene, let's see. I guess that. Is that 2 there, I think? 1 and 3. And hydrogen. Well, it tells you that this is an addition reaction. If it didn't tell you, how would you know? Well, you just got to remember, of course, double bonds, probably addition. You want to add stuff onto that chain. So H adds itself onto, onto this side here. H adds itself onto that side there of that double bond. That double bond breaks, add in the hydrogens, and of course you will get CH3, CH2, CH3, which of course is propane. Okay. B was, once again, propene. And iodine, I believe. And once again, what are you going to do with this reaction? Well, double bond, right? Probably easiest thing is to add those I's on either side there. So once again, I'm going to get CH2 with an I on here, CH with an I on there, and CH3. So in this case here, we'd have 1,2 diiodopropane. All right. And lastly here, we have propene again here, and hydrogen iodide. Now, once again, add the H and the I on. So I'll put the H on the first one here, CH3. CH, I'll put the I here. and CH3. And anytime, of course, you get ones that look like this, you have to ask yourself, does it matter where the H and the I goes? If I flip those around, in other words, if I put the I on the first one, and the H there, basically instead, is that going to make a difference? And the answer is it will, so you need to write out both, of course. Those are isomers of one another. This would be what? 2-iodo, oops, didn't spell that right. 2-iodo-propane, and this would be 1-iodo-propane. All right, so be careful of isomers, of course. Make sure you think about all the possibilities for those. Alrighty. Next, elimination reactions. Once again, elimination reactions, these are really the typical two here. Start with an alcohol. You'll see a catalyst for this one, sulfuric acid there. Didn't turn out very well. But butan-2-ol, so let me just write that out. Butan-2, I don't know, maybe I'll do it over here. Doesn't matter, I guess. Butan-2-ol looks like that. H3, that's got an H there, H2 and H3. And that's all it is. They tell you, of course, that it's butan-2-ol, and then they just give you this H2SO4. So, I mean, first of all, I think you can see there's nothing to add on there because first of all, there's no double bonds or triple bonds to add stuff on. You're not going to add anything on. Your other option, of course, is you could take stuff off, which is what we're going to do, or you could do substitution, but once again, there's nothing to substitute in there, so by default, I guess you have to kind of do elimination. Remember, the sulfuric acid there, that strong acid there, is to take the OH off and basically take an H off. Now, which H do you take? Do you take one from there or there? Does it matter? And the answer is probably does. That's why we're doing this one. So I'll take an H off the first one, and I'll take double bond there for CH. Okay, so this H is going to come off, this OH is going to come off, and that'll give me the double bond there, CH2, CH3. Obviously, I will get water here as well. So that's one option. Then you have to go back and say, well, what if I would have taken this H off and this OH off? Is that going to give me a different result there? And the answer is yes, it will. I'll leave a little bit of room here. CH3. If I would have taken, I'll leave that H there, of course. I'm going to take the OH off that one. And then the CH2, I'm going to take that H off there. Double bond there. Okay. And then CH3 at the end. I think that's right. Let's see. So I got 4 around each one. I think so. So this is but 1-ene, and this is but 2-ene. And of course, don't forget, you do get water as a product. Don't forget about the little things like water and whatnot, because of course that could be an easy multiple choice question for them to ask. They could say, you know, butan-1-ol undergoes elimination. What are the products of that? And they'll give you 4 different options, and probably in 1 or 2 of them, they'll probably won't put the water on. So don't forget that water is a product. H and OH come off there and join to become water. The next one for those is this one here, 2-chloropropane and potassium hydroxide. So 2-chloropropane and potassium hydroxide. And anytime you see potassium hydroxide, once again, you have to think, geez, you know, what am I going to do with that, right? Potassium hydroxide. Well, you're not going to add it on because there's no double or triple bonds. You're not going to do a substitution because, once again, what are you going to put on? What are you going to take off? You know, we know that, hey, K plus really likes Cl minus, right? Chlorine. So those two are meant to go together. That's what the potassium or the lithium or the sodium is there for. So you're going to get some potassium chloride, first of all. The OH is always there to, of course, go with H to make water. So where's the H going to come off of? Well, it could come off of this one here, or it could come off of this one here. In this particular example, because there's only 3, it's not going to matter. You're going to get the same structure either way. I'll take it off the first one, but you're going to get some water as well here. And finally, you will get CH2. I'll take the H off of that one. CH, okay. Again, don't forget, because you take an H off and a Cl off, you have 2 extra free electrons there. So that's where the double bond is formed right there. And then, of course, CH3. And let's see, does that all work out? I think so. That is called, of course, and we don't need to worry about Prop 1 heating or anything like that, because either way you're going to do that, it's going to be Prop 1 heat. There is only one Prop. Okay? You don't have to worry about putting the number there, because that's what it's going to be. Alright? So that's elimination. And then substitution here real quick, before we get into the little bit more complex ones. Substitution, once again, butane, yep. Yes, yeah, for butene, you could either do 1 or 2. Yeah, and then 3 would be the same as 2, and 4 would be the same as 1. So, but you would have to for that one. Oh yeah. If just because it's on the first one doesn't mean that you can skip it out. The only time you can skip it out if it's on the first one is especially cyclo, because you know that the first one is going to be that double bond no matter which way you decide to go. So that one for sure you can skip out. The small ones, like ethene, for example, once again, ethene's only got 2 carbons, so where the double bond can go is going to be have a choice. For propene, same thing. Where's the double bond going to go? It's got to go between either 1 and 2 or 2 and 3, which is really 1 and 2. But once you get the butene, then yeah, you have to worry. Yeah. Okay, butane and chlorine, okay, substitution reactions. Usually what you'll see here, and I don't know if you said this, you'll see a little bit of UV light here, so that's a good indication to help this reaction. These reactions are incredibly slow, of course, because, and then also, when you look, even if that UV is not there, for butane, I said, I think, okay, 2, 3, and I said chlorine, is that right? Now, even if that's not there, so pretend that that's not there, well, you know, once again, what are you going to do with this? Well, it's not going to be addition, because there's nothing to add on there. There's no double bonds or triple bonds to break, so it's not addition. There's nothing elimination. What are you going to take off? Well, what's the chlorine going to take off here? Remember, chlorine likes things like sodium and potassium and things like that, but there was none on it, right? So the only thing you have left to do here is to put 1 on and take 1 off, and that's, of course, substitution. So you can take, for example, do the old switcheroo with those 2. You could do the switcheroo with those 2. You could do the switcheroo with those 2, but of course that one would be the same as this one here. So you're going to have 2 isomers, of course, in this case. Don't forget, when you take the H off, though, the H combines with the Cl, so one of your products is hydrogen chloride. Okay, don't forget about that. The chlorine comes in, let's say, and I'll go CH2Cl. Oops. CH2, CH2, CH3. So that's an option. Of course, that's 1 chlorobutane. And the other option, of course, is if it goes on the second one there. That would be, of course, let's see here, CH3. I'll take the H off of that one and replace it with a chlorine, CH2, CH3, and that would be 2 chlorobutane. Okay? And, of course, hydrogen chloride as well. Once again, don't forget about that. Okay, so that's substitution. And sometimes you might get lots of isomers, and sometimes you'll only get 1. It really just depends. The next one here was, let's see, chlorobenzene. So there's your benzene ring there. And fluorine, fluorobenzene. I'll put the fluorine there. and fluorine. And once again, yeah, you probably should see a UV thing there, but not necessarily. If they don't, then you're just going to have to know that. Remember, this is benzene, so there's only one spot at each one of these carbons here. So remember, it's C6, well, usually H6, but in this case, it would be H5F. Now we're going to start putting F's on and taking H's off. So your first option here would be something that looks like this. That fluorine has to stay there, of course. I'm not taking that one off. That fluorine's not going to switch with another fluorine. That doesn't, and even if it did, it wouldn't. Okay. So I could take maybe this one off right there and put a fluorine on. So that's an option. I could. That's my original fluorine there. I could take this one off and put it on. An H off there. Put that one on there. I could, let's see, there's my original fluorine there. I could take this one off and put it there. And then once you get back to the next one, of course, they're all going to be the same after that. Okay. However, because of that, you do get a lot of isomers. And don't forget, once again, you know, when the F goes on there, the H comes off. So don't forget, you also get HF. Products there. Hydrogen fluoride, you're going to have, I don't know if I really want to write all these out here. This would be 1, 2, so where can I write that there? 1, 2 difluorobenzene. I'm going to cheat a little bit here. So 1, 2 difluorobenzene for that one. This one would be 1, 3 difluorobenzene. And of course this one would be 1, 4. 1, 4 difluorobenzene. Okay? Yep. Like another one. Yeah. So if it wasn't a benzene one, if it wasn't benzene and it was just that, let's say had your original fluorine there, well then, yeah, because now you have more H's here, right? So there is another H here. That could have got replaced with a fluorine. You could have put one here. It doesn't matter if you put it there or there, it's the same one. There, and there. And then of course you just have to worry about isomers. I think eventually you would run into the same issue with some isomers there, or the same thing, flipped over kind of thing. But you could technically, yes, there could be a fluorine that comes onto this one and an H that comes off that one. In that case, yes. But in our case it couldn't, because of course there's only, it's benzene, right? So, yeah. Esterification, always alcohol and propanoic acid, of course, and then this one here. So alcohols and carboxylic acids. So real quick here, let's see. What do we got? Ethanol. Ethanol, of course, is well, 2 carbons. Yes. So it looks like that. That's ethanol. Sorry. No, sorry, that's not ethanol. That is, I don't know, I don't know if it really matters to you guys if you want to do the acid first and then the alcohol, or vice versa. If you do the acid first, then the OH and H match up kind of thing, so it's kind of up to you guys. I guess maybe I'll do it first for the first one. Let's go with the acid first, which is actually propanoic acid, I guess. Propanoic acid, like that, and ethanol. I'll put the OH here. Ethanol is 2 carbons. That's a 2. Okay. So, propanoic acid and ethanol. Remember, always, and this is something you have to remember. It is the OH from the acid comes off, and the H OH from the alcohol comes off, and then it's squeezed together. Yes? So that's why it's kind of handy to write it like that. If you write it like that, that way you can just kind of squeeze it together, pretend that the OH and the H aren't there. And of course, you'll get, as a result, CH3, CH2, C, double bond O. This O is part of right there, basically, and then CH2, CH3. This is from the alcohol, that's from the, well, actually, technically, that's the alcohol part, I guess. And then, of course, the other part is the acid. So remember, when you go to name these, the alcohol part comes first, so this becomes now not ethanol, but now it's ethyl, space, 1, 2, 3, so propanoate for that one there, ethyl propanoate, okay? So you don't have to write them all like that, but then that way you can just kind of visualize it squeezing together, I guess. Might make it easier for you, I don't know, okay? What do we got here? 2-chloropropane-1-ol and 3-methylbutanoic acid. And I don't know, maybe we'll just stick with that. Butanoic acid here. Butanoic, that's 2, 3, 4. That's a 3 there. 3, 1. Remember, don't forget, once again, 1 carbon, 2 carbon, 3 methyl there. 1 always starts at the double bond there. This is H2H. So that's good. And 2-chloropropane-1-ol. So propane is 3. 1-ol, I'll put the OH here. That'll be carbon 1 there. And 2-chloro. So there. And then that will have to be a 2. No. 2, 3, 4, yeah, I think that's right. 1 and a 3 there. Okay. Once again, of course, the OH and the H come off. Squeeze it together. So, did I write that on the top one here, or did I miss that? I did, didn't I? Don't forget, when the H and the OH come off here, don't forget you also get water in esterification reactions. Don't forget that. Go back and fix that. So don't forget about the red part there, the water. Okay. Once again, that'll give you, I'm going to write it down right now so I don't forget, water. And, of course, once again, squeeze these together. So the reason I like writing them like this is because that way, I just copy down what I have on the left side here, and basically what I have on the right side. And we should be good, just a matter of naming them. So remember, the first part is always the alcohol part, so that's this part right here. That's a bond there. That, remember, is carbon 1 here, always starts from that O. 2, so 2-chloro still, and that, of course, that was propanol, now it's propyl. So we're going to go 2-chloro, propyl, space. So that was the alcohol part, 2-chloropropyl, and then of course, same thing, this is carbon 1 here, 2, 3 still has that methyl on it, so I'll go 3-methyl butanoate. Okay, is what we need for that one there. And I think we're almost done here. All right. Polymer is a very large molecule, of course, that's made up of many repeating units. The monomer is the small unit that will be used as a repeating unit. The name of the polymer comes from putting poly in front of the monomer. So, for example, if it was ethene, for example, if that's what you started with, it'd be polyethene. All right. A monomer contains a double bond. That's what needs to break and then form the next repeating unit, basically, right? So the monomer molecules join together through addition reaction pathway. So once again, you'll see on each one of these we have 2 electrons there, 2 electrons there, 2 electrons there. those are rearranged, right? So they kind of go like that, rearranged, and that's what forms the next bond to it, right? So here you can see the electrons are rearranged here, etc., etc., right there, and those can hook up, those can hook up, that one can hook up with the next one, etc., etc. Okay? So we started with the monomer here, of course, ethene. That's what you guys would call it. Don't worry about this ethylene thing here. It's ethene monomers, and of course the product of that, and once again it says this, don't worry about that. This is called polyethene, is the product. Okay? That's the polymer that you get from ethene, polyethene. All right? And it's a repeating unit. What that may look like, in fact, is something like this here. So you might have, let's say, CH2, CH2, and you may have an N basically like so. That's not a very good 2 there. CH2, CH2, something like that basically, which basically means we have many, many of those. And what do you get over here? You end up with CH, what is it? CH2, CH2, and once again, you'd end up with many of those, just as many. So if you had 1,000 of those, you'd end up with 1,000 of those repeating units. Okay? So you may see something like that as well. Condensation polymers, remember, usually, I'd be surprised if you even get asked anything about this, but it's only going to be probably something like this, where you know it's alcohols, of course. Usually very common is esterification one. Alcohols and carboxylic acids, right? So here's your, basically, you know, here's your repeating unit here, right? So that is, you know, your fancy acid there, basically your C double bond OH, okay? And here is your alcohol part. The thing with these is you have to remember that in order for this to continue, you might say, how do I know the, first of all, you don't have to know the names or anything like that, but how would you know that it's going to be a polymer type of question, or when you see this? Well, look, I mean, you know, the carboxylic acids we do usually are C double bond OH done. But we have this here and, of course, this here. We have the same thing on both sides at the ends. And the reason that's there, of course, is because that has to combine with an alcohol, which combines with an acid, which combines with an alcohol, which combines with an acid, an alcohol, an acid, an alcohol, an acid, an alcohol. So they need this stuff at both ends for it to combine together, basically, right? The reason it's called condensation, of course, is because you do get water, just like with any esterification reaction, you do get water as a product, of course. Esterification is the acid and the alcohol, you get H and OH and you get water. So that's what, like I said, I don't think you'd see something like that, but you never know, I guess. And don't forget, this is that ester linkage here, right? So ester linkage there. And that's what hooks the two of them together, of course, right? As always, OH from the acid, H from the alcohol, they come off, squeeze them together, and that's what you're left with there. Okay, well, I guess that's it, eh? Good, perfect. All right.